Welcome to Radar System course. Now we will continue a TACAN Tactical Air Navigation System. So in a TACAN navigation system that is useful for the military aircraft to find out what will be the range and the bearing information. Okay, so we consider that a ground TACAN station. Okay, so we have you can see that a ground TACAN ground station, and then in a aircraft. So in a aircraft they have the system so that will transmit the pulse okay to the TACAN ground station so transponder, then it will revert back the signal, and then according to that aircraft is able to find out the what will be the range. And then a TACAN ground system consists of a rotating antenna for transmitting a bearing information, and a receiver transmitter for transmitting the distance range information. So distance range information transmitted by this one means pulse interrogation there, and here a TACAN means it will provide you the a bearing information. Okay, so means you can say that a range as well as the bearing information, and that bearing measurements are obtained from the pulse signal transmitted by the a rotating omnidirectional antenna from this TACAN ground station system. So rotating omnidirectional antenna, just like we have seen earlier in AVO area. Okay, so you can say that this one is about the antenna. Okay, so it is transmitting the signal, so that's why you can say that a rotating omnidirectional antenna. Okay, so bearing measurements are obtained from the pulse signal, whatever the pulse signal transmitted by rotating omnidirectional antenna, that will be from the TACAN ground station there. And this omnidirectional signal, it has a fixed reference signal, so that's why we can identify what will be the start of each cycle there. So the because a fixed reference pulse that is to be useful for a reference bearing pulse there, and that will provide you the information regarding the bearing there. Okay, so generally some particular fixed signal it is to be transmitted, and then that will be compared with the main reference bearing pulse. Okay, so we can say that we have a TACAN signal, so we will consider how this stream of the signal is to be transmitted there. So because it has a TACAN ground station system, okay, we can say that a TACAN ground here, a signal is to be sent. So TACAN signal input to the ground station we have, antenna we have. So in that case, we can consider that a similar way we have considered earlier for this position or a location there. So this one is about, we can consider this one is a north and a south here, and this one is about a east and west. Okay, then we will see that a signal is to be transmitted, then we can say that a rotation. So from this main reference bearing pulse, so what will be the a TACAN directional pattern? So generally this one is about a center of this antenna, so it has a directional pattern will be likewise. Okay, this one is about a directional pattern of a TACAN there. So generally a TACAN antenna system, so it has a one driven element and all others are the a parasitic element, just like earlier we say that likewise the structures are there. Okay, so one driven element and another is about a parasitic element. So in another way we can say that we can draw this one is one driven element. Okay, so here driven element and all others are the a parasitic element likewise. So this one is about a driven element. Okay, and all are the a parasitic element. So this one is about a TACAN antenna system. So we can consider that a TACAN a system. So it consists of one driven element, and this one is about a driven element, and there are a total 9, okay, parasitic element. Okay, these are about the driven and a parasitic element. Now then we can consider that a at a ground station. So just like we can say that a airborne takeoff equipment, it consists of a interrogating transmitter and a receiver. So this one at a aircraft, and that will be useful for the air range there. Okay, so this one for the range there. So this one mostly it will be installed, that TACAN ground station can be installed at anywhere, and this can be installed in an airplane or a ship or a truck. Okay, so likewise, so we can say that a TACAN system that will be installed at any place there. So ground system will be different, and if you can say that uh, for the aircraft or ship, that will be a different one. Because whatever the signal is transmitted here from this aircraft, okay, so it does not have any encryption, so that's why it doesn't provide any security from the enemy identification there, and it operates in a UHF band. Okay, okay, so that's why we can say that it can determine the distance for about 100 aircraft simultaneously. This one is about a TACAN interference system. So generally we can say that a bearing is to be determined electronically by measuring the time lapses there. So for example, this one is about a reference plane. Okay, so you can say that a TACAN directional pattern of an antenna. And here, for example, suppose there will be the aircraft now at this particular position there will be. So what will be the, this one is about a east, this one is about a west, and for example, we can consider this one is about a north, and this one is about a south. So from this, we can find out, this one is about the position of the aircraft. Okay, so what will be the distance or from the east to this one? So this one is about the bearing information. Okay, so according to that, we can find out what will be the bearing information, in which direction signal is to be sent. So through this, a bearing information, okay, so can be obtained there. So bearing is to be determined by measuring the time lapse between the start of the main reference pulse. Suppose we can consider that this one is about indication of a start of main reference pulse, suppose, and this is rotating now. Okay, so this is moving. So in that case, the bearing information can be obtained. So where will be the position of the aircraft? So according to that, we can find out the a bearing information of the aircraft. Okay, so we have the a TACAN system that will be useful for identifying the location there. So we can say that this one is rotating. So how this pattern is rotating? So from the north we can find out, or from the east, whichever. So from whichever the place we are getting the stronger signal to the orbiter, and that will be useful for the identifying the what is the a position. Okay, that's about a bearing information. Okay, so this one is about a TACAN system. So this TACAN is useful for measuring a range as well as the a bearing information. Okay, so next navigational system will continue here, and that will be of a microwave landing system. Okay, this one we consider here microwave landing system. You can say that MLS. So in a microwave landing system, so it just use uh, what will be the a beam position. Okay, so we can say that signal is to be transmitted, and then what will be the position of the beam, because on a runway, okay, so there are the transmitter as a receiver, and from this a beam will be transmitted. So we can find out the what will be the a position of the beam here. Okay, so on a runway, the signal will be transmitted, and what how this beam is to be formed. So that is nothing but, and that beam information is useful for the a landing system. So it provides what will be the azimuth, okay, back azimuth, then approach elevation, and a range information. You can say that azimuth, then a back azimuth, then a approach elevation, and a range information. Okay, so these are about the micro landing system, and that will be useful to find out the what will be the azimuth there. Okay, and this back azimuth. Okay, so this one is about azimuth. So we can say that, so from the ground station here, suppose this one is about horizontal now for this antenna. So, and aircraft is here. So what will be the distance here? So in that case, so this angle is called as the azimuth now. Okay, from the ground, from the aircraft, and back azimuth, that will provide a guidance for the whatever the approach missed approaches here. And mostly, if you consider that a MLS system, uh, it operates a same frequency. It means we can say that a transmitter for the uh, azimuth and a back azimuth approach, both are the same. Means we can say that to find out the what will be the azimuth and approach. Okay, so or a back azimuth. So for both the cases, they are using the same frequency there. Then a elevation to obtain the azimuth as well as elevation. So we can consider a transmitter to be operate with the same frequency, and that will be useful for finding out the what will be the azimuth and elevation. So generally a elevation transmitter, so because on a runway, if you consider that this one is about a runway here, and then a azimuth and elevation. So on this particular runway, we can say that this one is about a center of a runway here. So on a runway, a elevation transmitter is located. Okay, so we can consider that on this particular runway, suppose here is a transmitter, you can say that a on this itself here, so there will be a transmitter there. Okay, so that will be useful for identifying the information. So elevation transmitter is present on a runway itself. So that elevation, generally elevation transmitter, generally we can consider that it is to be located on a side of the runway or at some particular threshold point of a runway here. So mostly people are considered at one particular position that elevation transmitter is to be located there. And that elevation transmitter is located on a side, or will be safe. So that will be located at about 400 feet from the side of the air runway here. And that will provide the range guidance. Okay, means this elevation, because we can say that it is useful for the azimuth as well as the elevation. So this it will provide the what will be the range there. So in this case, a, so two antennas we supposed to consider that will be useful for the identifying the azimuth as well as the elevation there. So azimuth and elevation type of antennas are used in a micro landing system. So in this case, vertical array of dipoles for the elevation. Okay, to find out the elevation. vertical array of a dipole. Okay, that is useful for the finding out the elevation there. Okay, and then we can consider just like you, we say that the antenna is a vertical or the antenna is horizontal. Okay, based on that, what will be the your electric field component? Okay, so if the electric field component is perpendicular to the ground system, so that's why it is called as a vertical antenna. If the electric field component is parallel to the ground system, it is called as horizontal antenna. So elevation, to obtain the elevation angle, so vertical array dipole antenna is useful here. Okay, so array of a dipole. So area of a dipole, just like we can consider that this one is about the area of a dipole, but their electric field is a vertical one, so that's why it's called as a vertical array of a dipole. That will be useful for the elevation scanning. And then for the azimuth, we can consider that again not a array of a dipole, but it is used a vertical slotted waveguide. Okay, this one is useful. So waveguide means what? This one is about your waveguide. Okay, this one is about the waveguide here. Now slots are provided at this side or at this particular position. These are nothing but the slots on the waveguide. So a vertically slotted waveguide that will be useful for the azimuth there. Okay, so means for the elevation dipole, for the azimuth we can consider the a waveguide there. So that's why we say that a two antennas useful for the identifying the elevations as well as the azimuth there. So mostly if you consider vertical array of a dipole or a vertical slotted waveguide antenna, that are nothing but the array system, and that array antenna, it consists of a radiating element, because we have array means nothing but a more number of irradiating, more than two number of irradiating elements there, and then that total system MLS array system consists of irradiating elements, phase shifter, RF power divider, and a beam steering system there. And this micro landing system operates in the range of 5031 to 5095.7 megahertz. Means it is in a gigahertz of range, and it has a 200 channels. We can say that we have, and that channels are spaced with, spacing between the channel is about a 300 kilohertz. Means channels are 300 kilohertz apart. Okay, so we can say that this MLS system, and information rate in azimuth is a 13 hertz. We can say that azimuth information rate that will be of a 13 hertz, and elevation rate, so information rate in elevation, that is about a 39 hertz. Means we can consider that a two information rate to identifying the azimuth and the elevation information, and both antennas are vertical, so that's why we consider that uh, vertical array dipole. So polarization is nothing but a vertical, because the antenna is vertical, so that's why a polarization is again a vertical one. Then how much the air range is covered by this particular MLS system? So for the azimuth and the elevation, so it covers a plus or minus 40 degree in azimuth, so 40 degree, that we can consider the azimuth, and a 0.9 to 1.5. Okay, so we can consider that 0.9 degree to 15 degrees in elevation. Okay, so that's about a Azimuthan elevation there. So the signal will, whatever the signals we say for this Azimuthan elevation, okay, so that will be transmitted at a signal frequency on a time sharing basis, and then it will provide a navigation guidance for the alignment and a landing of a aircraft, because the systems are installed or present on a runway there. So to land the aircraft, so this information is useful. So what will be the azimuth angle there and what will be the elevation? So mostly we can say that elevation, if you consider, so for example, we have the transmitting antenna here. Okay, so we say that antenna, and this one is about the aircraft. So in that case, what is the position? So that will be given by this azimuth there. What about the elevation? So elevation means what? From this vertical, how much will be the angle? Okay, so at the given particular position. So what will be the angle? So that's why we can say that we are getting the elevations from the system. So if we consider here, so likewise we can find out the elevation. So means we can say that it has signal transmitted that will be on a time sharing basis, and that will provide the information regarding the guidance for the landing of the aircraft there. And then its coverage area means that MLS coverage area is about the coverage area that will be 20 nautical miles. So means position, supposed to be aircraft is here. So what will be the position? So that's why we can consider that is about a elevation angle. So through the verticals, what will be the elevation angle? So likewise we can find out the elevation angle there. Okay, so generally we say that a MLS signal, so we can consider that it uses a Morse code there, and that Morse code consists of a 4 letter. Okay, so we can say that, and each letter it has a different uh, signal there. So we can say that a Morse identification consists of a 4 letter there, and then that particular letter will start with a M there, and then its code is transmitted, okay, for every 6, okay, so times per minute there, and then that particular 4 signal, because it has a 4 letter, so that's why a 4 signal transmitted means we can say that MLS transmits a 4 letter or a 4 signal, and then it provides that whatever the signal will be transmitted by the MLS there, so it provides the informations regarding the what will be the navigation one. Okay, so generally we can consider that it will provide information for the landing. It will provide the informations in terms of a weather guidance. Okay, so we can say that MLS system provides the all weather guidance information. Even it can be providing landing of the aircraft, or it can providing a landing in a small area or on a small building there. It has a 200 channels. So means we can say that uh, we can provide the information to the number of aircraft there. Okay, so and the guidance quality is a high here, and it does not require a service interruption. It has a low maintenance and a low cost there. So it can be adaptable to any type of aircraft, that will be a big aircraft or a small aircraft there. And the this provides the information regarding the lateral coverage, that is nothing but we can say that a azimuth, so that's why it is about a 40 degree lateral coverage information from the center. and it is located at about 1,000 feet beyond the air runway there, and it covers a height of a 20,000 feet with a reliability there. It eliminates a interference problem, okay, and it is this provides a safety and a economy. But if you consider a in terms of a disadvantages, it is very costly then, okay, and every instrument is independent unit, so that's why it will be a very costly. So mostly we can say that it operates to provide the information about the azimuth, okay, so we can say that it will provide the information in terms of azimuth, then a back azimuth and a approach elevation. Okay, so this one is about the information, and that will be obtained through the irradiating beam. So we can say that we have the runway now, okay. So this one is about a runway we consider. Then we can consider that is about the main beam here, just like a beam. This one is about a beam here, and then another beam that is about a scan beam. This one is about a scan beam. Okay, these are nothing but a scan beam. This one is about your beam, main beam here. Okay, so means we have a two radiating beam, and these beams are called as a scan beam, and that are scan beam that will provide the information regarding the azimuth there and a elevation there. So these are about the tool. So it transmits a signal at a same frequency. So this one is about the diagram for the beam, scanning beam and a runway here. So in that case, we can consider that when the beam is scanned, then the aircraft is located, and then position of that aircraft is to be obtained. So how to identify the position of the aircraft? So we can consider that this one is about a back azimuth, and this one is about a approach azimuth. Okay, and then we can consider that this one is about a elevation. Okay, elevation. So this one is about useful for the azimuth and elevation there. When the beam is scanned there, then the aircraft will be located, and then its angular position of the aircraft is equal to what? VA. What will be the timing? Okay, divided by A2 here. This phi is nothing but the angular position here, and this one is nothing but a angular speed of the beam while scanning in a degree per microsecond, and this di is about a time at phi, okay, whatever the azimuth at phi is equal to phi 0, and del t is what? A time interval between the to and fro scanning, okay, this is to and fro scanning, and through that we can find out the what will be the angular position. Okay, so this one is about a phi here. So that's all about a micro landing system. So with this we stop here. So we'll continue the discussion on the navigational system. So we remaining the few remaining navigational system, that is about a simplified directional facility SDF, then a long range navigation LORAN, and then we will see that DACA, TACA, that is about a hyperbolic electronic navigation system. Then we will see that a omega, and that omega is a very low frequency operated navigation system. These are about a four navigation system. We'll see in the next session. So with this, we stop here. So thank you all.